All right. All right. So I got 2:35. So today we are October 11th. We're going to finish off encapsulation and most likely start on linked lists. A bit of a quiet week. No tutorials due at the end of this week. No tutorial sessions during the week, although there are office hours. Next week, tutorial sessions resume. And I would recommend getting a start, even though assignment 2 is not due till after the break. I would recommend getting started on it next week at the very latest, right? So that you have the resources to ask questions. Yeah. All right. Other than that, after the break, basically it's going to be very, very busy compared to before the break. But any questions on the calendar? Okay. All right. So yeah. Last class we were talking about, so I do want to revisit, actually, we were talking about const parameters. So there was one thing that I didn't take up that a student mentioned, and I thought, you know what, that's a very good idea. So when we talk about const parameters, for instance, I have a student class here, and I have this move to function that takes an address. And specifically, it takes a reference to an address, because when we pass an object as a parameter, we should pass by reference. And if it's simply an input parameter, that is, we don't need to make any changes to it, then we should make it const, which basically makes it read only. We can't modify it. There are times, however, that you want to pass a pointer, or perhaps return a pointer. So if I, for instance, now this is going to make some of the syntax a little bit awkward, but I could change this to a const address pointer. Now, what does this mean? The way I say it sounds like it's a constant pointer, but it's a pointer to a constant object, just like the previous address was a reference to a constant object, right? So if I write it like this, it's a little bit misleading in that the pointer itself is not const. Okay, so the pointer itself is a variable. It has a value. That value is a memory address. I'm okay to change that memory address. What I can't do is change whatever that memory address is pointing to. Okay, so that's a subtle distinction, but I thought I would address it just in case some of you wanted to, implement something that looked like this. Of course, now home address equals address. Yeah, now I have to dereference that. Sorry, excuse me. But it's still, I can read from it. I just can't write to it. Sorry, pardon me. Okay. The other thing is that now this, I passed in an object, just an R value, right? Because I just declared this address. It doesn't have a variable name. I just declared it. Technically, that's an R value. Now, I can still pass it. I have to pass the address, though. So it's actually, I'm going to verify that this still works. But technically now I'm passing a pointer to a constant object. This address that I declared here is a constant object, and the ampersand makes it a pointer. But yeah, let's make sure that this still works. To be honest, I did not test it. And it's always a good idea to test, especially with C++. Well, oh yeah, C. All right, so this is not going to work. Taking address of an R value. Okay, so yeah, technically an R value doesn't have an address. But if I did something, for instance, if I made a variable that was const. Then I should be able to pass in, I think that'll work. Okay, now it's sort of happy, maybe. Yeah, okay. So yeah, const pointer is a pointer to a const object. It's not a const pointer. I can actually make const pointers. I don't ask you to do this, but if I changed this to here, now this is a const pointer, which means I can't change what it's pointing at. Although I can, sorry, I can't. So yeah, the pointer has an address. The address is what it's pointing to, so I can't make it point to something else. I can change the address at the end of that pointer, but I can't change the pointer itself, right? I'm not going to ask you to do any of this, but just so you're aware of the different applications. And if I had a double pointer, well, I could do all kinds of stuff. Right, so you can have stuff like that. So I have a const double pointer to a const pointer to an address, etc. Okay. But the main use that you guys might find for it is this case here. Questions? Okay. All right, so last class we had left off talking about friendship. I didn't quite get to we almost got to the end. We got to a really interesting case, or at least I think it's kind of interesting because I'm not sure exactly. I know what happens and I know the solution. I don't know why this arises. I was actually trying to look it up before class today and I couldn't find a satisfactory answer. However, we were talking about friendship, and just as a reminder, we had previously been talking about encapsulation and the principle of least privilege and protecting your objects, and then C++ throws friendship at you and says, well, if you want to get rid of all that stuff, you can, but you can make it exclusive between two classes, or at least from one class to another class. So I can, as an object, grant friendship to another object or to a global function. I guess not really on here, but so when I grant friendship to a global function or to another class, that class or global function has access to all of my members, even the private and protected ones. Right? So it's as if everything is public, but just to that class or function. All right, and so then we had talked about, so I'll just briefly go through these examples again until we get to the one we left off at. So again, we had the student and the address the same as before. Oh yeah, we left off with this little problem. So yeah, it's pretty interesting. But so I have a student class I have an address or a student class that contains an address, and I want to be able to use this move to function, which is going to change the member variables of my address class. So in order to properly access those member variables, I could make some setters, right, on my address, but setters are public. So that means anybody can set now the member variables of my address class, and maybe I don't want to reveal, maybe it's okay to reveal it to student because address works very closely with student, but maybe I don't want to reveal it publicly what the member variables are in case I want to change them. Right, and if I do change them, I'll have to change student, right? So when I violate encapsulation, I'm entangling these two things. Now how they're implemented depends on one another, and that can be a good thing. It can also be a bad thing. But so in my address.h, my address declaration, I declare that the student class is a friend of mine, and then in my student class, when I implement my move to, I have no problem. So if I, for instance, comment that out, and I go back here, then all of a sudden the compiler starts complaining that I don't have access to these member variables. So as long as the address class declares that the student class is a friend, then this is a legal function. Sorry, I'm still trying to figure out why this other error occurs, but maybe one of you guys has some insight. So the other thing we can do is we can have as mentioned, a global function, right? So this global function takes a student, and what I want to do is say that this student lives in this city, in this province. So I need two things for this function to work. So I'm accessing stu.homeAddress. Stu.homeAddress is, of course, a private member of my student class. So in my student class, I have to grant friendship to this global function. Again, in the student class declaration, not in the implementation. But that still leaves me with this problem. So it says these are inaccessible because, as mentioned, even though address is a friend of student and student is a friend of this function, that does not make address a friend of this function automatically. However, I can declare that this function is a friend of address, and you'll notice that we still have a problem. And this problem arises for, again, I can't really figure it out, except that it's the same problem that arises when I have, for instance, a student that references an address and an address that references a student. And then what happens is one of those, the header guards prevent me from doing both of those things, right? Because if I include, in my student class, if I include address.h, and in my address class, I include student.h, right? So let's say I did do that. Okay, so now, okay, so if I try to compile, const class student has no member named home address. Yeah. So something weird is happening here, but let's just walk through it and see what would happen in this case. So if I'm thinking like a compiler and I'm trying to compile, let me see here. Student does not name a type. Yeah. Okay, so here I've just tried to compile the student class. The student class references the address class references the student class. So I'm compiling student.cc. So let's start there and think like a compiler. The compiler reads these things, everything's fine. I import some libraries. It says include student.h. So right away, I don't read any more. I jump to student.h. I hit these header guards, and then I read, oh, go to address.h. I haven't read any student class yet. I go to address.h. I get here, it says include student.h. This, of course, goes back to student.h, hits the header guards, and returns right away. Okay, so in here, I've defined student_h, and then I jump to address.h. Address.h says include student.h. I come back, I hit these header guards. Oh, student_h has already been defined, so I jump back. I don't read that, right? So this is what the header guards do. They protect from multiple includes. But now when I get back to address, it doesn't know what this student is, right? Because I have not read the compiler has not read the definition of the student class. So when I have one class that references another and I include the .h, and then, so class A includes class B and class B includes class A, I get this sort of collision. So the solution is basically simple enough. I just say, in one of them, I'm going to forward reference the student class. I'm going to say, you haven't seen this class yet, or this type, but I'm going to tell the compiler there exists a class called student. So when the compiler gets here, it can say, okay, well, student is a class and a reference to a class is 64 bits. So I know the compiler knows everything it needs to know in order to compile it. So at this point, this should work. Yeah. Questions? Yeah. Sorry, could you?
Like if in that address dot h, if that include student dot h, and then
Oh yeah, I can definitely do that. I mean, it's here. Especially must have a class type, it has a class address const. Yeah, so this is just means we use the arrow here, and I mean I can. I'm not sure why I put it as a pointer, to be honest. I could just as easily get rid of it and then propagate all those changes, and then I'll still run into the same problem. I'm not going to do that because it's too much work, but yeah, that's just the pointer. For some reason, I forget why that was a relevant example at one point. Yeah, so here I go. Yeah, other questions? Okay, so that I'm allowed to compile the student class now. However, it still doesn't like this, even though it seems like I've done everything I need to do, right? This is a friend of the student class. It's also a friend of the address class. So what I have to do actually is, yeah, this. Actually, this solves both problems, right? So I forward reference the student class, and again, I'm not sure exactly why that because this is a problem here specifically where it's not a problem with just the address in the student class, and I'm not sure why. I tried to research it, but regardless, the solution is if you run into these where it seems like everything's included properly, but the compiler's not recognizing something, then yeah, you can try forward referencing. There's actually, so the way we do it, or the way I've been doing it, where I include student.h in my address.h, it's actually better to include that in address.cc. And if I include address.h in my student.h, I should include that in student.cc instead. And that solves most of these types of problems. But just to be aware of that there are these types of problems. Okay, so at this point, I should be able to move my students and then query where they are. And so Stu, I declare Stu and Joe, and yeah, Stu lives in Maine and Joe has no fixed address. Then they move, Stu moves to Vancouver and Joe moves to Montreal, Quebec. And then I call the where-to function, or the where function, and I'm able to access that information in that global function. Okay, so that's the main lesson about it. The other thing with the collisions and everything, that's a problem that you will, if you program in C++, at some point you're going to run into that problem. But yeah, questions? Okay. So yeah, that's it for friendship. Yeah. So in this friendship example, both classes required some knowledge of the other, but I can't include in student.h, I can't include address.h, and then in address.h include student.h because of the collisions. So one way to solve that is to forward reference one of the classes. And yeah, think like a compiler. Normally that's a good solution. In this case, that did not solve it for me, but yeah. Okay, so that brings us to static class members. So again, you're probably familiar with static class members from Java. right? So public static void main string args is a static member function of some class. So they have the same thing in C++. And basically, a static member, I have one copy of that static member, whether it's a static member variable or a static member, well, static member function, of course. There's only really one copy of a function. I just pass different arguments in, but for static member variables, I get one copy irrespective of the number of instances of the class. In fact, if there's 0 instances, I still have that static member variable. It's stored in the data segment of my memory map. So I can access it using the class name itself and the binary scope resolution operator, right? So we'll see an example of that. Or I can access it from any object of that class. Okay, so a static data member is a property of the class as a whole. So this value is shared by all instances, which can be useful for things like unique IDs and things like that. It must be initialized at file scope in the source file by convention. Modern versions of C++ there may be things you can do that are not exactly that, but that is sort of the traditional way to do it. The static keyword only goes in the class definition. It does not go into the source file when I initialize it, as we'll see. So it has static, again, like many things in C++, has multiple duties, multiple roles, and in this case, static means 2 different things, depending on whether I include it in a class or at file scope. So yeah. And in addition to static data members, I can have static member functions. Again, this is the service of a class as a whole, and I can actually call it even if there's no members of my class available to call it through. Yeah, and even though I don't call it on an object, I could still pass in objects of that type as arguments. And yeah, we specify it as static in the class definition, not in the source file, since that, I think the compiler complains. We'll see an example of that. So yeah. Okay, so I have a book class, again, an entity class. It has a unique ID, assuming I have a library or something like that, something very old-fashioned. It has a title and it has an author, and otherwise, nothing too fancy, just a print function. In my constructor, I initialize all the member variables. My copy constructor here, my destructor. Yeah, I think these will come in handy. And then I have a print. So all I'm going to do to start with, I'm going to make 4 books, print them all, and then we will talk about what we did and what we could do better using static members. Okay, so I made 4 books. I printed them all out, and then they all got destroyed. Okay, so if I'm a library, I'm going to give them each a unique ID, but this is very clunky, right? Especially if I have multiple locations, then I have to say, well, if I add a new book at this location, I have to, email you and tell you, oh, the IDs are now at this value. So, don't call your next book number 2 because I already used that number. Call it number 3 or whatever we happen to be at. So this is very inconvenient. You could have your 2 sections talk to each other and keep track of that, which is exactly what we're going to do, but we're going to do it with static members, right? So we're going to introduce in our book class a private static int called next ID. And this next ID now is an int for the book class as a whole, and it's going to keep track of this ID, the current ID. So instead of passing it in the constructor, I'm going to initialize it using the next ID variable. So at this point, I want ID is equal to well, assuming that I've initialized the next ID member variable correctly, I will set it to next ID, and then I will say increment this next ID. Okay. And then in my main function, of course, the compiler's unhappy. Okay, so now hypothetically, this should give me the same output as before, but now it's keeping track of the next ID automatically. The one thing that I didn't do actually is initialize this. It's possible the compiler would let you do this. No, okay, it's not going to. Okay, so depending on what version of C++ you're using, sometimes you can get away with stuff like that. So we're actually going to have to initialize this the old-fashioned way. And it is very important to initialize it, right? Sometimes it's 0, expect, other times it'll get 1,000,000 or negative 1,000,000,000 or something. So I'm going to declare an int. I'm going to use the scope resolution operator. And I'm going to initialize it at file scope in book.cc. Okay, so the same way that I'm declaring the implementations of all my functions in book.cc and scoping it in using the scope resolution operator, I do the same thing here. Okay, so this just says, as soon as I have a book, as soon as I define this book class, the compiler is going to reserve space for this next ID. And then when it compiles the book class, it's going to assign that space a value of 0. And then my first ID, well, actually, let's make it a 1. We want to start at 1. That would make more sense. Okay, so let's run it and make sure. And yeah, I get the exact same output as I did before. I have the member variables 1, 2, 3, or the ID numbers 1, 2, 3, and 4, but now they're assigned automatically by my book class. Yeah, so questions? Okay. All right. Let's say then I wanted to query what the next ID is, right? So maybe I'm making a new book, but I'm curious as to what the current number is at. So let's make a public getter for this. So I'll use the static keyword int get next ID. And I'll just do an inline function. Return next. Okay, so the static keyword makes this a member function of the class as a whole, which means that I can call this before I actually make any books, right? So at this point in my function, I have not made any books, but I can ask for the next ID using the scope resolution operator. Okay, and then okay, so my next ID is 1, and then I make a book starting with 1, and then 2, and then 3, and then 4. And then I print out all the books. And then maybe at this point, I want to get the next ID again. In this case, I can say b1.getNextID. I don't know where Java currently stands on this. You used to be able to do that in Java. It would always give me a warning when you did this, but I'm not sure if you still can or not. I'm way behind on my Java, but in C++, that's still allowed. Okay, so the next ID up here is 1, and then I make 4 books, and then I ask for the next ID, and I get 5 down here. Yeah. Questions? Yeah. Yeah, yeah. So there's a lot of possibilities. But yeah, definitely there, I mean, it's private. So you won't be able to see it in most cases, except for from like the next ID variable itself is private. So you can only really see it from the book class. If I made it a friend of another class, then yeah, you would have access to that. And it's subject to the regular naming collisions, right? So if I did introduce a next ID variable, there would be a naming collision, but I could always scope in book, the book next ID. So yeah, it behaves just like a regular variable, I guess. Does that answer your question? Or yeah, okay. Other questions? Okay. Okay. All right. So that is essentially brings us to the end of encapsulation. Again, so on assignment number 3, which is basically done, you will be doing some static member initializations and things like that. Yeah. So the next topic we're going to look at is linked lists. Now this is, linked lists in C++, so it has all of the basically properties of C++ or, strange going on and stuff. But essentially what this is now, we've finished the chapter on encapsulation. Right, so we've learned how to make everything private. We've learned how to use composition in light of this idea of the principle of least privilege and encapsulation. Basically, I want to, if I have a object inside my object, I want to call on those objects' member functions and not try to take shortcuts or, get data behind the scenes or something. We've talked about constants, so how we can protect our classes and functions and variables from changes that shouldn't be made. We talked about friendship, so when we throw away all those rules and then make 2 classes friends, and static class members. So this is still under the technically an example of encapsulation, but linked lists basically is a rich source of examples of a bunch of these things. Maybe not the static class members so much, but everything else, encapsulation and composition and things like that. Okay, so yeah, encapsulation and access, abstract interfaces. So we're going to make a linked list. We already have sort of an abstract data class, right? An array that holds students. So we're going to make a linked list that holds students, and we're going to basically reuse the same interface. We're going to have all the same functions. We will talk about how to separate data from the containers and keep them separate, right? So we want, now that we have sort of have this category of collections, we want to keep data worried about data things and collections worried about collection things. And how do we do that in a linked list? And of course, memory management in a linked list is sort of a big deal. So yeah, up till now, we've been using, well, we used raw arrays, and then we used array-based collections. Array-based collections have some disadvantages, although probably not as many disadvantages as you would think. But essentially, if we want to resize them, they're a pain because you have to basically delete your old array and make a new array and copy everything over. If I add or remove to the middle of an array, that's a bit of a pain because I have to shift everything over if I want to keep the same order. And these are things that linked lists are good at. So essentially, a linked list is a bunch of data items that are linked together. These data items could be in separate places in memory, but I have one data item point to the next data item, point to the next data item, etc. So what do we want to do? We want to link all this data together And then we want to figure out how, since we've linked all this data together, how do we do these standard operations like add, get, remove, and traversal. So traversal is going to be sort of the core of a lot of these methods or functions in a linked list. Okay, so the nice thing about linked lists as compared to array-based lists is that we allocate only the memory that we need. If we have a reference to a node, so we're going to talk about the structure of it in a second, but basically if I know where I want to insert something, it's easy to add or remove it. But of course, the key is I need that access. The data is not contiguous, so access can be slower. So the nice thing about arrays is everything's in a row, so I can just jump to the middle if I know exactly the index I want. In a linked list, I can't do that. I have to walk from one object to the next in order to find what I'm looking for. So yeah, linked lists require traversals. So that's one of the drawbacks of them. But when you get right down to it, they're both kind of useful. They both have their strengths and weaknesses, and a lot of data structures that you actually use combine linked lists with arrays, right? In some way that makes sense for whatever they happen to be doing. Okay, so a linked list, we can break it down into components. Of course, we have our list class and our data class that we're going to be storing. Now we want to keep these separate. Again, our data class should only be concerned with what data it's storing. And our list class should only be concerned with how to store these data. So this would fall under the collection object type, and this would be an entity object. So we don't want to modify the data class to allow it to be made into a list. So what we need is an abstraction layer between the list and the data. So we do want to store the data in different places in memory, but how we do that specifically is we introduce this node class. So this node class acts as the sort of abstraction or communication layer between my data and my list class. So the node class knows something about the data, and the list class knows how to manipulate the node class, and that frees up the data to just do what it knows how to do. Okay, so our linked list structure is going to look something like this. We have our list class. Our list class is going to have a pointer, which we're going to call head, and this will point to the front of the list. Down here, we have our student object, our data class that we're storing. And then in between the list class and the data class, we have our wrapper class, right? So this is a node. This is our abstraction layer. This bridges the gap between the data and the list, right? So we have a pointer here that points to the data, and we have a next pointer that points to the next node in the list. And then, yeah, sometimes we have a tail. This can be helpful for things like a queue. We'll talk about some variations. Okay, so why do we separate them? Well, again, for encapsulation reasons and abstraction. So the wrapper is an abstraction layer for each data element. Now my list, I don't care what kind of data I'm storing, I just manipulate a node, right? So I can write an algorithm based on that node, and then I never have to change that algorithm. I can change what the node points to, but that shouldn't change anything fundamentally. The list elements, the data elements, only need to know about themselves. They should not know anything about the data structures they're being stored in. If they know something about the data structures they're being stored in, then I can't change out an array for a list or a list for an array or any of those things. All right, so yeah. And, you know, I guess it's easy to see why we need the node class if you consider, well, what if we put a next pointer in our student class? Well, that has some drawbacks. For one, each student can only be stored in one linked list, right? If I had two linked lists, then I would need two next pointers. And if I changed the data structure implementation, I have to change the data class, which is not good encapsulation. So yeah. Okay. So our list class will look something like this, right? I have my list class declaration, and then I'm going to take a bunch of functions from my current array class, and those will be my member functions. So I want to have the same public interface as my array so that I can drop, I can take out one and drop in the other without changing my algorithms. And then I'm going to have a member variable of a node that points to the head of the list. Yeah, sometimes we have a tail pointer as well. And so this type of structure means that anytime I want to do something in my list, if I want to implement one of those functions from an array, I'm going to have to use a traversal. So sometimes we traverse an array if we're looking for something specific, or sometimes we can jump right to the point where we want, but in a linked list, we always have to traverse. Okay. As mentioned, what type of interface? Well, we tried to make a generalized student array class, and the interface looks something like this. So we're just going to reuse this. We want to keep it as general as possible. Right? We want to have the same face, different implementation in the background. Yeah. Questions so far? All right. We'll get to some implementation in a second. So I'm going to have a class called node, right? As we saw in our diagram, this node is going to have a pointer to a student, data, and a pointer to a node, next node, right? So this makes it a recursive data structure. And all that means is that my class node has a pointer to something of the same type. I only want the list class to know about the node, right? It's a private implementation detail of my list class. So I really don't want this node to be public. It's a private structure for my list class. So what can I do here is something we haven't really talked about, but yeah, okay, well, we'll get to that, I guess. So the node class is a wrapper for our data, supplies the list functionality without modifying the data class. We're going to hard code this data type for now. In the future, we will apply templates to this so that we can use any data type. And all right, that's enough of that. Okay, so linked lists in general may consist of a sequence of nodes with a pointer to the next element. We can have doubly linked lists, so we can have pointers in each direction, which might be part of your assignment 3. I haven't quite decided yet. We have a head pointer, which points to the first node, possibly a tail pointer to the last node. You can think about why that might be useful. Sometimes there are dummy nodes where if I have a linked list, instead of, I have my head pointer. Oops. And then I have a bunch of nodes containing data. And then at some point I have a dummy node, right? So instead of a null pointer, it points to some fake node that, and this is sometimes useful for things like recursive functions, or there's various other reasons why you might want one. I don't think I'm going to stand by this. We might have dummy nodes. I do want to make a few changes, so you have to implement something in a linked list on your third assignment, but haven't quite figured out what. Yeah, but if we don't use a dummy node, then what we're going to have is, well, how we're going to know we're at the end of the list is that this points off to a null pointer. Right, so my head points to some node that contains data, and this is the next pointer. The next points to the next node, and so on. And then finally, the last element, the next node, points to null pointer, and that's how I know I've run off the end of the list. Okay. All right. So I have these slides in some weird order. Getting back to the point where I was 5 minutes ago. So we want a node class, but we want this to be private. to our list class. So what we're going to do is we're going to make an inner class of our list class. So, right, so everything that is not in, after a declaration of public or protected is private by default. So this node class becomes private to the list class. So only the list class can make a new node, access nodes, and that allows us to make the member variables public. So then I have immediate access to them. So in some sense, this is like it's basically a struct, right? This node is just a student pointer and a node pointer crammed together in memory. Right, and then we can make the node members public, so the list will see them, but since the node is private, no one else can see the members, and no one else can make a new node unless they make a different class. So yeah, let's get to our example. Okay, so I have the students that we had before as our data members, our entity class. We have the array class that we used a couple lessons ago, right? So this is an array-based array class. So I have a dynamically allocated array of student pointers here. And in my array.cc, I of course initialize size and elements. And then when I add, I of course walk through the array and figure out where to put it, make some room, and then copy it in. Get, again, I find the thing I'm looking for, get at an index. So we're going to implement all of these now for the linked list. But to start with, what we want as a public interface for our linked list is basically this. We want to have the same interface as our array class to sort of enforce this idea of collection abstraction. Okay, so this I will change to list. Okay, return size. So get size we should implement as well. And then privately, as we talked about, we want to have, well, first of all, we want a node in here as well. So let's and this will hold students. Okay, so this is a private node class. And let's and then I will make a head pointer that points to the head of my list. And sure, we'll keep track of the size as well, just to be consistent with the array class. Okay, and this is one complaint, which is what? Okay, so that's our linked list declaration. So we have our private node class in order to sort of bridge the gap between our list and our data. And we have all of our public member functions that we're going to functionally do the same thing as the array class. So yeah, questions so far? Okay, so the first thing we want to do is, well, everything that we are going to do, add, remove, get, in a linked list requires a traversal. So we're going to start by implementing a traversal, and we're going to do this on the easiest function possible. Apparently my pen doesn't work, which is, we'll start with the print. So what does a print do? A print starts at the head. It prints the data in the head and then goes to the next element. So I start at the head, I follow the data pointer to the student. I print out that student. I have some pointer, let's call it current, that is pointing here, and then I point current to current.next, and it's going to point to the next node in the list. I go down to the data, I print out that student, current equals current.next, and so on and so forth. So a traversal is simply, I'm going to walk through my list, and in this case, I'm going to print every element. Okay, so let's start actually with our constructor. So we know we have a head. Want to make sure that we have an empty list, so we're going to assign it null pointer, and our size we'll say is 0. We'll get to the destructor later. For now, we will start with the print. Okay, as mentioned, I'm going to start at the head. I'm going to walk through the list. Of course, what I don't want to do is take the head and say head equals head.next, right? Because if I do that, I can print out the first element, but then I call head equals head.next. And what happens? Well, I'm at my next node, and I no longer have a reference to my first node, right? I can't follow a pointer backwards. So this node becomes a memory leak along with the data, right? So I want to make sure that my head always points to the head. So I'm going to just declare a temporary node pointer, and I'm going to use that to point at each of these nodes in turn. So node current equals, and we'll start at the head. And then I want to traverse the list. So if I just walk through the list without printing anything, I'm just going to repeatedly call current equals current.next until current is equal to null pointer, right? Again, I want to make sure that the end of my list is pointing to null pointer. So I'll say while current is not equal to null pointer. Okay, and this will walk me through the entire list until I get to the end, as long as I've implemented everything else correctly. So that is a basic traversal. And then, of course, we want to print everything along the way. So I'll just say current data print. Okay, this is a safe call because I know that current is not equal to null pointer. So it's pointing to something, it's pointing to real data unless I made a mistake somewhere. So I can access the data member variable and print it out. Okay, so that, and we'll just announce that that's what we're doing. So yeah, that's our print function. That's a very basic traversal. Any questions? Okay. All right, so now, not only do we have a print function, we have a traversal, but we have something we can test once we start writing our add function. So we have to consider, so a linked list, the devil is in the details, and there are a lot of itty bitty details, and it helps to make pictures basically. But when we want to insert in order as defined by the student less than function, the same as we did for the array class. So we have a less than function and we have an equals function. So this is going to tell us what order to store our students in. And we have to consider 4 cases and each one might need a little bit of tweaking of our algorithm. So case 1, I'm going to add an element to an empty list. Case 2, my list is not empty, but I'm going to insert something at the very beginning. Case 3, which is sort of the canonical case or the usual case, I insert an element somewhere in the middle of the list. In case 4, I insert an element right at the end of the list. Some of these might be easier than others, but we have to make sure that each of these is covered. Okay, so case 1, of course, we are starting with an empty list, so it makes sense to make that our first call. So we have a call to add students on an empty list. So we have a pointer that we want to store. So the first thing we need to do is make a new node, right? So every student gets its own node in the list. Once we do that, our head is pointing to null. Well, basically all we want to do is point it to our new node. Make sure our new node.next is pointing to null or null pointer, and that's it. So the first case is kind of simple. All right, so let's implement that, and then we can test it out. Okay. So what did we want to do? We want to say, well, if the list is empty, we want to add right to the beginning. So we'll say if head is equal to null pointer. Well, in this case, my list is empty, so I'm going to make a, actually, whatever happens, we have to make a new node, so let's do that. Right? We're making sure to use the new keyword here. We want this node stored on the heap so that it stays there until we delete it, right? We don't want to just declare a local variable that's going to get deleted when we exit out of here. Each of these nodes exists on the heap, so they're there for as long as we want. My new node data is going to be Stu, so I'm going to store Stu in this new node, and I want to make sure that right, since I didn't really, I could have put a constructor for my node class, but I didn't. Again, it's more of a struct than a class. But since I didn't put a constructor, I have to make sure that I initialize these members. And part of that is making sure that next is pointing to null pointer unless I change it to something else. Okay, so at this point, head is equal to new node, and I can return true. All right, so actually the one thing I'm going to change about this is I'm going to change these Booleans to void. So my list technically does not fail to add a student unless I run out of memory. And if I run out of memory, then the program's going to crash anyway. So at this point, I can always assume that this succeeds. Okay, so that's what I have so far. This should implement this case here. So let's see. Okay, so far so good. All right, so let's see what my main function does actually. Okay, so right now I have an array called COMP2404. I make a new student Stu, I add that to COMP2404. That's my array-based list here. And then I add a bunch of other students and I print them out. And then I remove a bunch, but we'll skip all that. We'll just make sure that. So at this point, my array-based list works fine. I add a student Stu, and then I add Zeke after Stu, and then I add Harold, and then Amy, Betty, Dexter, Timmy, all those guys. I should delete them, but this is sort of a demonstration of how the add function works on my array. And now at this point, I want to change that to a list. I've included it here. And you'll notice that because I have the same interface that the compiler is perfectly happy at this point, right? So all of the functions for list and array are the same. So technically, all of this should work if we implement it correctly. We know at this point, though, that we're only certain that we can add one student, or at least we want to test that we can add that one student. So we're going to comment the rest of this out, and then try that again and make sure that stu prints correctly. All right. Yes, we do actually need, the compiler is going to be picky and insist that we have a destructor. For now, I'm not going to do anything in the destructor. We'll come back to that in a second. Okay, so printing my list of students, stu gets printed out, so it looks as if my traversal works so far, and my add to the beginning works. You know, nothing's gone wrong yet, at least. Questions so far? Okay. So now we want to add another student, and well, so yeah, we could add to the front. That might be the, but let's think about actually the middle case first. We'll implement that, and then we'll go back and make sure that we'll tweak it for case 2 and case 4. So let's consider what we have to do for the middle case. As mentioned, adding something, if I know where, if I have a reference to where I want to add it, is somewhat easy. But first I have to figure out where to insert it. So I have this call here to add my student C. And we know how to do a traversal. I make a pointer. I point it at the same thing head is pointing to, and I say, right now at this point it's the same as the array. I say, is C less than A? The answer is false, so I'm going to advance. I'm going to say, is C less than B? Again, the answer is false, so I'm going to advance current equals current dot next. And then I'm going to say, is C less than D? The answer here is true, so I found where I want to insert my student, right? Okay, so I have a pointer to current, and I have a pointer to the head. And at this point, you know, this is going to keep getting deleted, but I make a new node. I put student in it, and then I want to insert that node into my linked list by redirecting this pointer down here and my new node dot next to here, which is where my current is pointing to. I have one problem at this point. So I have a reference to current, which means that I can say current dot next, you know, I can say that to do something. What I don't have is a reference to here, right? So I need to say this previous node dot next. I need to point that to my new node instead of my current node. And this is a singly linked list, so I don't, if I had a doubly linked list, I could just grab it. But I have a singly linked list, so I need to introduce a second pointer, which I'm going to call previous. Okay, so now my traversal is going to be slightly more complicated, but if I want to remove or add, well, yeah, remove or add, I'm going to need to keep track of the previous node. So now my traversal is going to look something like this. Current points to head, previous points to null. And then if I say current equals current dot next, before I do that, I'm going to say previous equals current. You know, these are backwards, but previous equals current and current equals current dot next. And then if I advance again, I'll say, well, previous is equal to current, and then current equals current dot next. And then I I say, is C less than D? The answer is true. So I make a new node, and now I have access to the previous node and the next node, and I can insert new node just by redirecting these pointers. Okay, so that's what we're going to do now at a programming level. Okay. So I want a traversal, but I want to have two pointers. Current equals head, and previous is equal to null pointer. And then it's going to be very similar while current is not equal to null pointer. So while I'm still looking at something and I haven't run off the end of the list, well, just to make sure, I'm going to, because I always forget to do this, in order to advance, I'm going to say, well, previous equals current, and current equals current next. Okay, so that's my traversal. And then here I have to do my tests where I ask if stu is actually less than the current data member. So if stu less than current dot points to data, and that data is a student pointer. So yeah, I actually have to dereference that. Right, so less than takes a student reference, and this returns a student pointer, so I have to dereference it to get back the pointer. Okay, this is complicated enough in any linked list. In C++, it's particularly complicated, but all right, so if stu is less than this, then I found my current is pointing to the place where I want. So I have my previous and my current, and in between I want to put my new node. So I'm just going to break out of here for now. Okay. All right, questions so far? Okay, so what did I do over here? I said, assuming now that this is going to work, my previous dot next is equal to new node, and my new node dot next is equal to current. So that's exactly what I'm going to write. Previous equals my new node, and my new node dot next is equal to the current node. So this is inserted my new node in between those two nodes. Now, again, we have to make sure this works for all of the cases, but this is the, I guess, in some sense, the common case, the most common case, or the case that basically where the most things I have to do happens. Okay. All right, questions? All right, so let's see if we could actually test it out right now. And just for fun, let's see if we can crash it. So we added Stu, who's next? Zeke. This might actually work. I'm not sure. Can't remember. So this is actually going to be if we add something at the end. So yeah, sure, let's try it. Let's live a little dangerously. Okay, so it looks like Stu and Zeke are added. Now, maybe that works, maybe it doesn't, because I would have to add a couple more to make sure that, you know, Zeke is pointing to something to null like they should. But yeah, so let's go over this case. So we have previous, we have current. If we're adding to the last location, what happens? Well, previous is pointing to null, current is pointing to the head. I call add C. Is C less than A? No. Okay, so previous is equal to current. Current is equal to current dot next. Is C less than B? No. So then previous is equal to current. current is equal to current.next, which is null. So in the algorithm I wrote, at this point, I would exit the while loop. Okay, so if I look at list.cc, as soon as current is equal to null pointer, I no longer execute this, which means that, of course, I don't get a seg fault here. And when I exit, well, previous.next, so previous is pointing to, well, at this point in my, right, so at this point, we've added Stu here, and then we've just added Zeke here. So previous is currently pointing to the node that contains Stu, and then I add Zeke to the end. So to add Zeke, I say previous.next equals new node. That's fine. New node.next equals current. Current is equal to null pointer. So my new node.next is pointing to null pointer, which is exactly where I wanted to end up. Right. So yeah, if we go down to the next slide, this is my Stu. This is Zeke. Zeke.next is pointing to null, which I want. This is my Stu here. And in this example, head is pointing directly to Stu. So it printed out fine, and it looks as though everything has worked out exactly the way we want for this case 4. So we have case 1, we have case 4 we've tested. Case 3 should work. Case 3 is where we insert in the middle. So let's try inserting another student in between Stu and Zeke. So here. All right. So Harold alphabetically comes between Stu and Zeke. Oh yeah. So as mentioned, the less than is alphabetical. So yeah, this should work. Seg faults. Okay. Something's wrong. That's interesting. Oh no, sorry. Harold goes at the beginning. So sorry. Add first doesn't work, but let's say we did Timmy first. Timmy is actually between Stu and Zeke alphabetically. Harold was at the first. So we know that the adding to the front doesn't work, but this add to the middle should work. Okay, so yeah, Stu, Timmy, and Zeke. So yeah, adding to an empty list works. Adding to the middle works. Adding last works. Adding to the front has problems at this point. But we'll walk through that example and see if we can identify where the problem is. But questions so far? Okay. So let's go back to add first. Okay, so this is our, we tried to add Harold here. Stu was at the beginning. Zeke was at the end. So when we added Harold, what happened? Anybody know why we got that seg fault? Just offhand? Or take a guess? All right, well, let's walk through it. We had previous that was pointing to null, and we had current that was pointing to head. The code says, is Harold less than Stu, right? So is student less than current node dot data, and it returned true. And so I exited, right? So if I look at the code for that, I made a new node. I initialized current to head and previous to null pointer. And I said, is Stu less than the current data? And the answer was true. So I broke out of here. What I didn't do was advance it all. So I didn't do any traversal. I just stopped right away. So that means previous is pointing to null pointer. So down here, when I called previous dot, arrow operator next, it gave me a seg fault because it said previous is not pointing to anything, and I tried to access something. Okay, so previous is equal to null pointer. That's the problem. So let's fix it. If previous is equal to null pointer, what do I want to do? I just want to say, head equals current. Sorry. Nope. So now, at this point, I want current to be the head of the list. So I could point the head pointer to current, but before I do that, I have to say current.next is equal to the previous head node. And if that head happened to be null, that's okay. And then I want to say head is equal to current. Otherwise, I can do this. Okay. Now this is quite big, and there's probably ways to compress this, right? There's probably ways to put a bunch of operations together and maybe only make one call to one of these. New node.next equals current. Sorry, new node. Yeah. Okay. But yeah, again, correctness is more important at this point, right? So maybe this is redundant. Maybe I didn't have to do all of this. But the nice thing is I've tested these individually and I know they work. So if it's correct, that is the most important thing. Oh, whoops. So let's change Timmy back to Harold. And now Harold is going to be inserted at the front of the list, and let's make sure that works. Nope. What happened? Okay, well, let's. Well, it is sort of always more fun when things go wrong. So added Harold. Harold did not get added. So I missed something. Oh, anybody see the problem? Yeah, so when I sort of dyslexiaed myself into writing current there, I also wrote current here. So shouldn't be current, it should be new node. So if previous is equal to null, that means we didn't go anywhere in the list, which means I'm inserting new node at the front. Otherwise, I went somewhere and I can insert new node in the usual way. So yeah, now finally I got Harold, Stu, and Zeke in the correct order. And allegedly, that is all of the cases. So if I add a bunch of other students in some arbitrary order, yeah, I get Amy, Betty, Dexter, Harold, everybody in alphabetical order, no seg faults. So all of my add cases are covered. Maybe not the most efficient code, but a correct code, which is the most important thing. So yeah, questions? Okay, so that's it for today. I guess, yeah, that's it for this week. So no tutorials due this Saturday. Tutorials are next week. And we'll talk about the midterm next week as well. Yeah.